We have so far covered fabrication of ceramic shapes by pressing, slip casting and tape casting. Today I will start off with what the title of the lecture is, extrusion. You have seen high density polyethylene pipes which are used for carrying water, the water lines. They are long tubes, they are extruded. Now those HDPE pipes, they are made from pure HDPE. But let's say I want to extrude an alumina tube. There I have solid loadings of about 80%. Polymer is hardly 10% or 15%. And hence, though the very basic principle of ceramic extrusion is same as that of plastic extrusion, yet there are many other issues which need to be handled. But before I start on ceramic extrusion, I would like to go through 3 or 4 YouTube videos which explains how plastic materials are extruded. I would start off with one and sequentially take them one after the other.
Now let's look at the inside of an extruder to see how it works. The plastic raw material in this hopper travels by gravity to the feed throat and drops onto the rotating screw. The rotation of the screw conveys the plastic forward through the heated barrel. As the plastic is conveyed forward along the screw, the channel depth decreases, forcing the plastic through a smaller area. The combination of compression and screw rotation causes friction which generates heat. This is called shear heating. This heat, along with the heat from the barrel heating system, melts the plastic. By the time the plastic is conveyed to the end of the screw, it should be well mixed and at a proper temperature and pressure needed by the die. The plastic is called a melt at this stage. Beyond the screw, there can be a screen pack. The screen pack is a set of wire mesh filters that the plastic must flow through. The screens are typically from 20 to 100 mesh, which indicates the wires per inch. The screen pack is supported by a breaker plate, which is a sturdy metal plate with many holes for the plastic to pass through. The screen pack filters contaminants from the melt. The screen pack must be set in place with a coarsest screen next to the breaker plate, so each screen can support a finer one. Otherwise, the pressure difference may break the fine wires, contaminating the product and possibly doing permanent damage to the die.
Well, this was the first one which showed how basically an extruder works. Now let's see what we have over here. You see, in many cases,
while there are many ways that a twin screw extruder can be designed, most in use today are either co-rotating, fully intermeshing compounding extruders, or counter-rotating, fully intermeshing pipe and profile extruders. There are 2 types of counter-rotating extruders, parallel and conical. The screws of a parallel extruder have the same diameter from end to end, while the screws of a conical extruder change in size, growing larger toward the feed end. A twin screw extruder looks simple and rugged, but it is a complex machine that can be easily damaged. To simplify this complex machine, we'll break down the extruder into 5 systems and look at them separately. These systems are drive, feed, screws and barrel, the adapter and die, and the control system. Because there are similarities as well as differences between co-rotating and counter-rotating extruders, we will make it clear which one is being talked about. The drive system consists of an electric motor that is coupled, either directly or indirectly, to a gearbox that has two output shafts along with a thrust bearing for each screw and couplings that connect to the screws. The motor is equipped with a variable speed drive that must accurately control the RPM, or revolutions per minute, of the screws from a slow crawl to full speed. Most machines have a mechanical overload coupling between the motor and gearbox. Many different types of motors and speed controls are in use, with the choice being based on accuracy, cost, maintenance, and horsepower requirements. The gearbox reduces the motor's speed and multiplies its torque or twisting force. The motor may turn as fast as 3,600 revolutions per minute, while screw speed may range from 30 RPM in a low-speed profile or pipe extruder to 1,800 RPM in a high-speed compounding extruder. The gearbox is strongly built and will operate without much attention if the oil is kept clean and is not allowed to overheat. Some operators are responsible for checking the oil and the oil temperature, a task that must be performed as scheduled. On some extruders, the motor is connected to the gearbox by belts. It may be possible to operate the extruder without the guards in place. This must never be done. Behind each screw there is a thrust bearing, whose job is to prevent backward movement of the screws when there is pressure in the melt. There can be a great deal of force acting to push the screws back. In a 3.5 inch or 90 millimeter profile extruder operating at 3,000 pounds per square inch of melt pressure, there is a force of nearly 13 tons trying to push each screw out of the back of the extruder. Thrust bearings are designed for a certain lifespan at a specified load, and their life can be cut in half by a 25% overload. This is one reason that the melt pressure must never be allowed to exceed safe limits. Nearly all twin-screw extruders are star-fed, although the feed flights may be just filled in some pipe and profile extrusion. In star feeding, the amount of material entering the extruder is set by how much is delivered by one or more feeders. Each feeder must deliver a smooth, steady flow of material, both to provide a consistent rate of output and to ensure that the proportions of the ingredients remain the same. In addition, the flow of material into the extruder must not be restricted in any way, a problem that can occur if the materials must pass through a pipe or duct after being measured out by the feeder. Feeders are normally equipped with a hopper, and material flows from the hopper to the conveying section. Gravimetric, or loss-in-weight feeders, deliver material by weight, constantly checking the amount being delivered against the setting. Volumetric feeders run at a set speed, so if there is any variation in the amount of material that flows from the hopper down to the belt, screws, or auger, the output of the feeder will vary. Gravimetric feeders can sound an alarm if their output changes, but volumetric feeders cannot. Feeding problems can include bridging, funneling, and separation of the ingredients. In bridging, fluffy, soft, or sticky materials that do not flow easily may form a bridge at the bottom of the hopper. The flow may stop completely, or the bridge may break up and later form again. Funneling is also caused by materials that do not flow easily, although it may be made worse by a hopper whose sides make less than a 60-degree angle. The material along the side stops flowing, and the material in the center feeds until there is a hole or tunnel through the center of the hopper. The feed may then stop, or the tunnel may collapse and then form again. Either way, the rate of feed to the extruder will not be consistent. There is another problem that affects feeding when the material that is being fed is a powder. A great deal of air is present in the material as it enters the extruder, and most of the air is squeezed out by the screws and flows back out through a vent below the feeder. It should not be allowed to flow back through the feeder and hopper because it can cause changes in the weight of material that is entering the extruder. Melting, also called fusion, should be nearly but not fully complete before the material leaves the compression section and enters the vent section. Insufficient fusion will allow powder to enter the vacuum system, while complete fusion will interfere with the removal of gas and vapor at the vent. In either type of machine, trapped air from the feed and gases or vapors from additives must be removed from the plastic before it enters the die. Venting is done by releasing the pressure on the melt, usually with vacuum applied, while constantly mixing the material. Any bubbles in the material will expand and break as they come to the surface, releasing the gaseous material. Co-rotating compounding extruders often have several vents. Whenever the processing conditions permit material to move into the vent section at a faster rate than it is conveyed out, material may flow out of the vent. This is vent flow, vent flooding, or some other descriptive term. In counter-rotating extruders, high melt pressure ahead of the screws is one cause, especially if the screws are worn, but there are many others. In co-rotating extruders, vent flow can be related to the screw design, screw wear, feed rate, screw RPM, and other factors. When the barrel, adapter, and die have reached their set temperature, wait for the required length of time before starting the drive. Never attempt to start the screws if there is any unmelted plastic in the extruder or die. Many newer extruders have a soak timer, which prevents the screw drive from starting until a preset time has passed after the temperatures have risen to their set points. As soon as it is safe to do so, start the drive at the specified speed and start the feed. In compounding, start only the main polymer feed. Don't let the extruder run empty for more than a short time because it causes rapid wear on the screws. As plastic flows into the extruder, watch the drive amps or percent load as well as the melt pressure gauge. If either one exceeds the normal startup value, find out why. Do not let it go because there may be a problem. If the motor amps or percent load are normal and the pressure is within safe limits, allow the screws to turn at the speed shown in the instructions. During this time, do not permit anyone to get in front of the die for any reason because hot gas and plastic could spray from the die. Once plastic is flowing from the die, gradually increase the screw speed. You may be required to let it run at some lower speed until the material is flowing smoothly from the die. If smoke, black material, streaks, or snapping or popping sounds continue, there may be a problem. If they clear up in the normal amount of time, thread up the line and start the downstream equipment if it is not already running. As soon as possible, bring the line up to production speed and closely monitor both the process and the product. Because it may take a large extruder as long as 2 hours to achieve consistent temperatures, continue to monitor closely until the process is stabilized. Don't make changes to the settings unless you are certain the process has stabilized, unless those changes are part of the procedure. Take the readings that are called for by the standard operating procedures or operator instructions and check them against the run sheet or setup sheet.
Well, you saw how a single screw and a twin screw extruder works. I brought in the twin screw extruder, especially the countercurrent one, because when I'm extruding ceramics, it may be a tube, it may be a rod, it may be a brick, it may be sheets. I am going to mix the hard ceramic powders with the polymers, and hence in such cases countercurrent twin screw extruders help in mixing of the ceramic in the polymer. You have already seen that in the last video that it may take up to a couple of hours for uniform mixing of the polymer, and they were talking only of extrusion of plastics. So, in ceramics the problem should be more difficult. Let us see what happens in the next one. Here I would like you to really look at how this is an animation, but how an extruder works. In ceramics, when we are extruding long lengths of pipes or tubes or sheets, it is very essential that the composition remains same right through. Yes, the particle size is a very important factor. The viscosity of the polymer, the nature of the polymer is a very important factor. But then we have to mix them, and so as to ensure that we can find the optimum mixing conditions, it is best that you really know now how the inside of an extruder works, because without it one will never be able to really ever understand extrusion. Well, you saw in the first slide over here and over here how the extruder moves and how they force. And in the previous one, you saw how the extruder blades move. It is not only that the extruder is being heated from the top, but again the motion of the polymer between the blades and the extruder, they cause shear heating. I would like to focus a little more on twin screw feeder. Is
twin screw feeder from above at 14 RPM.
You see, this is a twin screw feeder and I have frozen it at a particular point. See how the blades are. This twin screw is rotating in the same direction. Just watch.
RPM is set to 14.
They are rotating in the same direction. They are rotating in the same direction. When we are mixing with ceramics, what happens is that this polymer chains have to be really torn so that the ceramic powders do get wet by the motion of the screws. If you look at this screw, if you look at this screw, look at the spacings. This spacing is very important for polymer extrusion, and if we have a hard ceramic powder, you should understand how carefully these screws must be placed, especially because they will be working in a counterclockwise direction. Now, let us see a full 3D demonstration of how a pipe manufacturing unit works. Here the melt comes in, and now let me go back. You see, I want a tube, not a solid rod. So look here, what is there? There is a spruce die which forces the melt in this direction so that we get a pipe. The pipe has already come out of the die. It is now being merely labeled and numbered, nothing more. So I go back again to this point here. When I want a pipe, not a rod, a spruce die is put in the flow path of the liquid so that the liquid now flows, and now it has come to a cooling zone. It is still flowing. Because of this spruce die over here, instead of a rod, we get a tube. So you have seen in one slide how we make rods. There was one animation graph. You have seen how in the last one pipes are made, plastic pipes. Now let's take up real ceramic extrusion. First of all, as I said, in this one, if I have to extrude ceramic, I have to have 80% loading, 80 weight percent loading of ceramics, and about 20% polymers. So the mixing is very, very important. The type of mixers that are used in ceramics while doing ceramic extrusion are something like this. This has got distinct similarity with what you saw in polymer extrusion. Here is the pug mill chamber. Here is where de-airing occurs. Why? Because whenever, let's assume you have taken a bucket of water and you are rolling your finger in it, you will see bubbles in it. So when in this pug mill chamber, the ceramic particles and the polymers are being mixed, especially if there is a counterclock motion shaft, there will be a very large amount of bubbles which are being generated. So in this particular case, we have a de-airing hosier which is connected to a vacuum pump, so that the air bubbles are removed from the polymer ceramic mix before it is extruded. So this section is very important for de-airing. The polymer ceramic melts comes in. Now it is again similar to the plastic extrusion. It comes to this auger and here it is extruded through this die. Now, there are various other options also available. Like say, let me take this. I don't have the money high enough to have this sort of a mill. What I could do is, I could mix the ceramic with the polymer, and then what I could do is extrude it using this simple technique, where I have got the ceramic polymer mix. This is which is heated, the billet, the ram moves in, and the extruded product comes out here. Now, this is something which is possible and has been tried very extensively. Now, we go back to the first diagram. Because this is the most useful one. In pug mill, what is it that happens? Here, premixing of ceramic plus polymer occurs. This is the first thing that occurs. Here, at this particular point, we add to the ceramic the binder, the plasticizer, dispersants, and even flocculants, lubricants. All of these are added. This is added to this pug mill, where counterclockwise rotating blades, they shear the polymer, as you saw in the first video, mixing the plasticizer helping in the shearing, the dispersant, flocculants and the lubricants dissolving in that molten polymer, the ceramic powders being coated with the dispersants and the flocculants, and the pug mill. What does this do? Needs the premix. Now, the best simile I would say is, if you have seen your mothers prepare chapati or you prepare the chapati, you take the dry wheat, mix it with powder and keep on kneading it till it becomes very soft. Now, what happens in the chapati that you make? You have taken the dry wheat, ground wheat and the water. What happens is the water hydrolyzes the wheat grains, causing them to swell up and let the polymer chains flow one past the other. That is kneading, and that is precisely what is happening in the pug mill, where the polymer is being rotated again and again and again, so that they have got a soft, homogeneous, premix of ceramic polymer material. This is fed to the extrusion chamber from where the material is extruded. It can be extruded in the form of rods, tubes, bricks, sheets, anything. It has to be a long, continuous, uniform size sheet. Now, as you saw, the rods being chopped off to manageable pieces, the tubes being chopped off, manageable pieces. Bricks is a long rectangular piece which comes out, it is chopped off at appropriate intervals. So, the ceramic extrusion is similar to extrusion of polymers, but with a lot more riders. As I said, due to the heavy ceramic loading, mixing of the ceramic with the polymer is a problem. Abrasion is a problem because the ceramics can abrade, and hence we have to be very careful when we extrude a ceramic. Now, let us take a couple of issues during extrusions. What can be the issues that may cause a problem? One is that I had written over here soft homogeneous premix. Why? So that flow is uniform from the nozzle. Flow is uniform from the nozzle. If I have this over here still, yeah. You see, they are making a polymer pipe. This is polymer pipe. It's easy, but now let's presume this is really 88% loaded ceramic polymer matrix, and this is being forced through this thin area. What would happen if mixing is not good, if the matrix is not soft, if the flow is not laminar? I would have lot of defects at each of these points. I would get non-uniform flow over here, and as a result, these non-uniform flow which I get will be reflected also in the property of the pipe which is over here. Hence, in ceramic extrusion, this requirement that the mixture must be plastic enough, homogeneous enough to flow under pressure is an absolute statement. Is an absolute statement. This is 1. 2. Again, mixture must not stick wherever. It should not stick to die walls, any tool like the spruce which I had used, because if it sticks, I will have a non-uniform flow. Third, this is something that is very, very important. The fluid or the molten polymer must not separate from the ceramic powder under pressure. That is, they should not form different phases under pressure, which can happen in many cases. If the ceramic powder is not properly wetted, if the powder is not compatible with the polymer, they would separate. Separate means what? The ceramic would agglomerate, the polymer would agglomerate, and I will not have a homogeneous extrusion. Fourth, this is during post processing. If I go back to the slide, albeit very briefly, you see this pipe which is coming out, this is basically a polymer laden, a ceramic laden polymer pipe. It is still not a ceramic pipe. To do that, what we would have to do is, presuming this is the ceramic polymer matrix I am extruding, what would I have to do? I would have to burn this polymer, this whole tube which you are seeing over here, in a furnace, cause binder burnout and do a sintering of the ceramic powders. So, essentially, if this is the pipe which has come out, if this is the pipe which has come out, which is polymer 80% ceramic by weight and 20% polymer, in order to convert it to a ceramic tube, I would have to burn all the polymer out, have the ceramic grain sinter, so that I get a real tubular ceramics. This is the post processing, that is sintering. Now, if you go back to my earlier one when I was talking of sintering of ceramics, I did say that the binder we use should be as small as possible and clean burning, so that the gaps between the particles was not this big. I would prefer particles to be like this, with the binder forming only a thin layer. Why did I say that? I said that only to ensure that the distance between the grains which have to sinter is small, because as the distance increases, either the diffusion time increases or the diffusion temperature increases or both increases, and frequently if the distances are too large, effective sintering does not occur. I had said that earlier. Now, here in this ceramic extrusion, I have got 20 weight percent polymers. If I convert that into volume percent, 80 weight percent alumina divided by force, the specific gravity. So, if I have got an alumina polymer matrix, where the ceramic is 80 weight% loaded, volume percent ceramic is 20% and the polymer is 80%. So, here I am telling you that I have a situation which is so unlike which I had asked over here. Here I have got substantial polymer separating the ceramic grains. Hence, a major issue is these green ceramic pipe, these green polymer matrix ceramic pipes, where ceramics may be 80 weight% loaded, but in reality it is 20 volume percent. I have to be able to burn off the polymers very cleanly and yet have polymers which draw the ceramic powders together so that effective sintering takes place. What does this mean? It means that if I have, let us say, this thick dia polymer ceramic pipe, remember it is 20% ceramic, volume percent ceramic, 80 volume percent polymer. So, its thickness will reduce by that amount. So, I will expect heavy shrinkage. The size shall reduce, the thickness shall also reduce, because 80 volume percent polymer is being burnt off, leaving behind 20 volume percent ceramic powders to sinter. Hence, the thing is, the burning of must be reproducible across batches, implying that the shrinkage, which you cannot avoid because a large amount of polymer will burn off, residual porosity, C, ash content or carbon content, they are all reproducible, not only in one batch, from batch to batch to batch. Otherwise, no one will buy the product. You can never stabilize your material. This is very, very important. And this is one of the biggest problems of ceramic processing, ceramic extrusion. It is not only the polymer, not only the shrinkage, also the flow properties, or what they also called rheological properties. These are very, very important. You see, in most of the cases, a polymer processing person will always want a Newtonian fluid. He will always want a Newtonian fluid, and I cannot blame him, simply because he wants to assure that the flow is uniform rate at a uniform speed. He does not want the flow rate to vary as a function of pressure or anything. So, he wants it to be Newtonian. Here the polymer is flowing in a lamellar fashion. We put in ceramic particles unless these ceramic particles are wetted by the polymers, there will be vortices, there will be turbulence, and hence this rheological property has to be very well controlled by choosing the binder, there is a polymer, the lubricant, the deflocculant very, very carefully. One has to choose that. Of course, the nature of additives which are added depends on the type of powder you are using. I won't debate that. If, let us say, I want an alumina tube extruded. In one case, I want it for use at a maximum temperature, say in a electrical generation in a super thermal power station, where the temperature will rarely exceed 400 or 500 degrees centigrade. That is one area. On the other hand, I want the same alumina to be used to fabricate a tube which will be used to pump in oxygen into molten iron, where the temperatures for a fraction of a second shoot up from 1700 to 3000 degrees centigrade. The alumina which will be used in a super thermal power station will not be heated to more than, as I said, 500, 600 degrees centigrade. So, there the best additive for alumina is kaolin. This is an excellent binder. I talked of kaolin earlier at the start of the class. They are thin platelets, hardly 10 angstrom thick, 100 angstrom across, and they form excellent binders for alumina tubes. However, the problem is due to the presence of silica, it may form low melting phases. So, if I am using kaolin as a binder for alumina tube, I can jolly well use it below 1000 degrees centigrade. Nothing will happen. But this certainly cannot be used to fabricate an alumina tube which will blow oxygen in molten iron or steel, where the temperature shoots up to 3000 degrees centigrade. If I am going to fabricate an alumina tube through which I can blow oxygen into molten steel, I cannot afford to have any glassy phase. So, there the binder has to be an organic binder which will not form a glassy phase. You see, there are various types of organic binders which are available. Let me take this paper off and let them focus on it. Yeah. Now, I had talked of many of these. For example, I had talked of PBA, I had talked of gum arabic, I had talked of starch, acrylics, methyl cellulose, this one sodium alginate, polyacrylamide, guar gum. While doing slip casting, tape casting over there, the amount of binder was very, very low, but here the volume percent of binder is very high. So, one has to look at what is the viscosity range of the binder. For example, if I got a very low viscosity binder, I have to be able to work at very low temperatures of extrusion. But if my processing requires much higher temperature, maybe for the lubricant or whatever, one has to come to this particular area. And these are the binders which one has to choose from depending on your system. If you have got alumina, any of these, because all of these are, I have got hydroxy group, any oxide can be used for with these binders. And the problem will come if we have, instead of oxides, we have got carbides. Then which binder to choose? That becomes a problem. In that case, what we frequently do is we functionalize the ceramic powder so that it is compatible with the binder. Means if I got SiC, I will have to adsorb some organic molecules on top of it, which will also be compatible with the polymer matrix that is out here. This is called the functionalization. When I come back after this for the next class, I will talk of the compositions of different bodies which can be extruded, what are the different compositions, before I continue further with the extrusion. Thank you.